we present CoGS, a state-of-the-art method that enables the direct manipulation and re-animation of Gaussian splatting scenes. Given an unstructured image collection of deformable objects from various views and poses, our goal is to create a controllable Gaussian splatting scene capable of rendering new, unseen views and configurations. This project is heavily reliant upon the original Gaussian splatting pipeline, in where SFM points are used to initialize a set of 3D Gaussians parameterized by position mu, rotation r, scale s, the color c, represented via spherical harmonics, and opacity alpha. The Gaussians are then projected from 3D to 2D and rendered via a highly efficient rasterizer. During optimization, the density of the 3D Gaussians is adaptively controlled to best represent the scene. This iterative process yields a high fidelity reconstruction, setting a new state-of-the-art benchmark in the field. Recently, this work has been extended to the dynamic domain. One such method optimizes all parameters for the first time step, essentially performing static reconstruction. Then, for subsequent time steps, all parameters except the color and opacity are incrementally optimized. This approach, combined with numerous loss functions to further constrain the scene, allows for accurate reconstructions and smooth movements over time. Despite its impressive performance, it requires a multi-view dataset consisting of 27 training cameras. Another method, published simultaneously with ours, uses an MLP to learn positional, rotational, and scaling offsets for each Gaussian over time. While this method only requires a single camera setup, it cannot achieve a controllable 3D Gaussian splatting scene. CoGS completely removes the prohibitive camera setup requirements and overcomes the inability to achieve a controllable Gaussian splatting scene found in prior works. First, we learn a dynamic Gaussian splatting scene. Then, we perform 2D to 3D mask projection to determine which Gaussians are associated with specific scene attributes. Using this, we can determine signals to gain fine-scale control over the dynamics of selected regions and render entirely unseen configurations. For the first phase of learning the dynamic scene, we directly extend the static Gaussian splatting method. For the first 3,000 iterations, our focus is exclusively on learning the static elements within the scene. After this warm-up period, we extend the original method with separate MLPs to learn offsets for each parameter across time. Throughout this process, we impose multiple losses to strengthen geometric consistencies, resulting in state-of-the-art reconstruction quality. The next phase is to control portions of the learned dynamic scene. To do this, we first perform 2D to 3D mask projection to select Gaussians we wish to control, obtaining masks M0 through Mn, one for each control region. After obtaining the masks, the positions mu are then projected onto the primary movement direction determined by principal component analysis. This allows us to define the start and end points along the movement direction, providing separate control signals for each masked region. Using these signals, an attribute offset is predicted and the masks are applied to affect the designated regions of the scene. This process allows for any dynamic scene to be controlled with fine-scale signals. Here we present dynamic results on a synthetic scene. Notably, CoGS demonstrates superior quality in modeling fine details, such as the wrinkles in the clothing. This improved performance is even more apparent when the videos are paused, and we focus on the face. Unlike other methods that produce blurry outcomes, CoGS delivers significantly clearer and more detailed results. On real scenes, we also observe improved performance. Compared to other methods, CoGS generates more accurate reflections and cleaner boundaries between the red shell and the yellow chicken. For this scene, our method also shows superior quality, better modeling the knuckles on the hand. With CoGS, any dynamic scene can be controlled. Here we show controllable results showcasing completely unseen dynamic configurations. For more results and details on this work, visit us at CVPR or check out our project page. Thank you so much for listening.